this is Xiaohang. Today I'm going to present our work supporting large language model generated programming feedback validation at scale through user attention-based adaptation. This work is done with my collaborators and mentors, Sam Wang, Zicheng He, Dr. Yalong Yang, and Dr. Yan Chen. When learning to program, personalized feedback is among the most effective ways to help students bridge the gap between their current understanding and their desired learning goals. Growing class sizes make it difficult and even infeasible for instructor to deliver personalized feedback. Where large language models offer the potential to generate personalized feedback at scale, their reliability remains a critical challenge. And consequently, instructor validation is a necessary step to guarantee the quality of feedback provided to students. Yet, this validation process itself imposes a significant cognitive burden that instructors need to evaluate large volumes of code feedback pairs and mentally shift between different contexts. Prior work on large language model output evaluation explores supporting user sense-making process of large language model outputs at scale and evaluating large language model with user-defined criteria. Previous research also worked on creating code feedback at scale with a large language model validator and through teachers created code repairs. However, the challenge of cognitive continuity in sequential review tasks remain unaddressed. So to understand instructors' needs and workflow they use when authoring and validating large number of large language model generated feedback, we first developed the initial probe system and conducted a formative study. The probe system allows instructor to author and review feedback using large language model in both a systematic way and at scale. So let's look into the probe system. And so the probe system groups students' code submission based on common errors and displays the number of students within each group. And each piece of feedback is generated using a template with 5 components: issue, strategy, solution, example, and next step. Participants can easily toggle each component on or off depending on their preference. We also incorporate text highlighting to support instructors' validation process. So with this probe system, our formative study reviews 3 primary behaviors in reviewing and revising large language model generated feedback at scale: managing cognitive load during context switching, identifying important content efficiently, and reusing revisions across similar feedback instances. Based on these findings, we came up with 3 design goals to guide the design of our tool. First, the system should facilitate a seamless review process based on user attention. Second, users' revision actions should be reusable. And third, the system should enhance interface support for the flexible revision. Guided by our design goals, we designed and developed REVA, a human AI system that expedites instructor review of large-scale AI-generated program feedback. REVA has a 3-level validation adaptation workflow, including user attention and data characteristic-based adaptation. When no user specification exists, REVA clusters and sequences the submissions based on submission context. And when users have an implicit specification of their attention, for example, revision, REVA first analyzes their action and propagates them to applicable code feedback pairs. Meanwhile, when users express explicit specification of attention, for example, filtering, REVA extracts and semantically matches user attention on unreviewed pairs and renders the review panel accordingly. All these three adaptation methods contribute to the review sequence in the order of priority. And let me show how REVA can help instructors with a quick demo. Let's imagine Bob, an instructor of a large introductory level programming class, who wants to give comprehensive feedback to his students for this week's coding assignments. So he starts the feedback task with great scope, but quickly realizes that he has to switch between multiple issues back and forth, which is very effort demanding, and he's giving similar feedback to multiple students, which is very redundant. So instead, Bob decides to try REVA to streamline his feedback process. After uploading the student's code submission to REVA, Bob can customize his feedback generation with component-based prompts. And within seconds, REVA provides specific feedback for every submission. We see that REVA color codes each feedback component based on its category in the prompt, making it easier to identify key information at a glance. As Bob reviews the generated feedback, he spots a common misconception about variable naming. He can use REVA's semantic filter feature to track this misconception across submissions. And by selecting the exact code that represents this error, Bob creates a semantic filter that shows him how many submissions match this pattern and highlights relevant code lines, which gives Bob a better understanding of how widespread the issue is throughout the class. And after creating additional filters to support his review process, Bob returned to the feedback. Upon closer inspection, he decides some revisions are needed. REVA offers multiple ways to make changes, so Bob can either interact with the feedback, the code, or the task itself, or simply tell REVA what he wants to change by direct prompting. And REVA also displays revision suggestions with inline changes. After Bob accepts the revision suggestion, REVA then automatically applies this revision to all applicable submissions and reorganize the review queue to match Bob's attention patterns. Based on his understanding of the student misconceptions and the class overall progress, Bob can also adjust the feedback component and their level of abstraction, as well as direct edit feedback manually. So after titerating feedback to match his teaching style, Bob moves to the next submission. He noticed that this code looks familiar. He wants to give similar feedback to this code. And then he says that REVA has already prepared revision suggestions based on his previous edits, ready for his verification. Using the visual connections between inline changes and revision summaries, he quickly applies the appropriate changes and continues reviewing the remaining feedback elements. Bob can feel the review process accelerating. With REVA's flexible revision interaction and user attention-based feedback validation adaptation, Bob completes the validation process efficiently and provides his students with timely and comprehensive feedback. To evaluate the effectiveness and usefulness of REVA, we compared REVA with a baseline version, which does not have the semantic filter and revision propagation. Users still have access to all individual revision features and the predefined filters. And so the evaluation with 12 participants in a within subject study and annotating the sample dataset of their feedback, we found that REVA helped participants make more revisions. Meanwhile, instructors produced feedback with better issue coverage and overall quality. We also observed that REVA kept participants more engaged across validations. And this is the end of my presentation. Please read our paper for more details.